All right. Hello, everyone. Welcome to week 18. This week, we talked about some more kind of hardware related stuff. Specifically, we talked about error correction and how we can use error correction to make our qubits better, right? Because today's qubits are not perfect by any means. And it would really be a bummer if we had to wait until our qubits were perfect to be able to do any type of quantum computation, right? So we are really focusing on this thing called quantum error correction, which allows us to use our qubits to perform quantum computations without needing absolutely perfect qubits. So, this week, as usual, we will have a notebook and a homework quiz. But the first few questions of the homework quiz have nothing to do with the notebook. So, we're going to go through those first, then we'll switch over to the notebook, and then we'll come back and finish the homework quiz. So, let's get started. The first question is, what is the name of the set of 5 criteria that describe the ideal quantum computer? This one's just a memorization question. The answer is Di Vincenzo's criteria. There are a whole bunch of things that he says that quantum computers should have, in order to be considered ideal. So some of these are scalable. We should be able to add more qubits to our quantum computer. We should be able to kind of initialize qubits to an initial state. We should also have really long decoherence times, meaning the qubits should retain their information for a really long time. We should also have a set of quantum gates that can transform any state into any other state. And that's super important because we don't know what quantum circuit we're going to want to run on our quantum computer. So making sure we could bring any state to any other state, make sure we could run literally any circuit we could imagine on our quantum computer. And then the last one is measurement. We should be able to measure our qubits. So those are the kind of necessary characteristics that a quantum computer should have, and these together are called Di Vincenzo's criteria. Question 2 asks, why is error correction necessary? And I gave kind of a hint about this at the very beginning. It is because enough errors can completely derail our quantum algorithm. We see this with some specific super sensitive algorithms like Grover's algorithm. If there is an error while we're running Grover's algorithm, it actually completely messes up our state. Sometimes it makes it so that we can't even find what we're looking for. So we want to correct these errors and make it so that it doesn't actually affect the state we're working with. And we do this through error correction. So the correct answer here is that enough errors can destroy any use of quantum computing. And just to add to that, I gave the example of Grover's algorithm where even one error will mess it up. But there are other algorithms that are a little less sensitive to errors. And we'll be talking about some of those in upcoming weeks. But with enough errors, we kind of lose our ability to trust the quantum computer, right? It's like if the weather person came on every day and 50% of the time they gave you the wrong prediction of the weather. Then you would really start to lose trust in the weather person's abilities, right? You wouldn't know if you're able to trust what they're telling you or if you need to do your own research and figure out what the weather is on your own. Something similar happens here. If the quantum computer gets the wrong answer more often than it gets the right answer, then it's kind of pointless to have this super kind of expensive piece of equipment that's just going to give us the wrong answer. I mean, I could give you the wrong answer to any problem you want. It's not that hard. So error correction is necessary to make sure our quantum computer is able to function even though its qubits aren't perfect. All right, so that's that for question 2. Question 3 asks which of the following best describes the relationship between logical qubits and physical qubits. So just as a quick review, logical qubits are the qubits that actually kind of perform our computations. They are the ones that we really care about. These are the qubits that we want to protect the state of because they have a really important role in our quantum circuit, right? We're performing our operations on those logical qubits. Whereas physical qubits are not necessarily something we care about. The physical qubits oftentimes are just there to protect the state of the logical qubit. And so, in general, physical qubits will encode a logical qubit state and will, at least in the error correction circuits that we're going to be talking about today, they serve to protect the state of the logical qubit. Yeah, that's kind of all I got for you there. So physical qubits encode a logical qubit state, usually with the purpose of protecting that logical qubit state. All right. Moving on to question 4. Complete the following sentence. A syndrome measurement is one that blank. So this first one I think we can eliminate right away. I don't think a syndrome measurement makes qubits sick. But what it does do is it detects errors. A syndrome measurement is one that we take to check if there was an error or not. So the syndrome measurement is one that detects errors. It doesn't cause the errors, and it doesn't correct the error. It just tells us if there was an error or not, which even that is really valuable information, right? If I tell you the weather and I say I'm absolutely correct, I'll give you $1 billion if my weather prediction is correct. I'm probably not going to want to take that deal I'm offering it. But that's a bad deal for me, right? Because me making a guarantee that I didn't make any errors is really, really bad. But if I said, hey, I'm allowed to make one mistake in my prediction, and then I'll give you, or like if I'm still wrong, then I'll give you $1 billion. In that case, having that extra piece of information that I made an error makes it easier for me to trust myself, right? I get the result of my prediction. So even if I made one mistake, it's totally fine. At least I knew about the mistake, and so I can kind of get away with it, right? Or in this case, I would correct it, right? Maybe that was a really bad example. But knowing about an error is often really, really valuable information because errors don't immediately tell us that they happened. They kind of sneakily mess up our results, and we won't be able to tell just based on our results if there was an error or not. So if we know that there's an error, we can go in and correct it. But if we don't know about it, then we're going to assume that the result that we get is absolutely correct when it may not be because of noise or errors or whatever else it might be. So the correct answer here is that a syndrome measurement is one that detects errors. All right. Finally, question 5. Given a bit flip repetition code that uses 100 qubits, what is the maximum number of bit flips that can occur before the error fails? Or the error correction fails, I think it means. So how these repetition codes work is if one of the qubits makes a mistake, that's not a big deal because we have kind of a group vote at the end of our circuit where all of our qubits vote on what the correct state is. And whatever the majority, whatever state the majority of the qubits are in, that's the state that the logical qubit is going to be corrected to. So for example, if all of the qubits at the end are in the one state, then the logical qubit is going to be put in the one state as well. However, once we get to a certain point, if enough of our physical qubits have errors as well, and they're not in the state that we want to correct the logical qubit to, then the majority decision is going to be wrong. If all of our qubits make an error except for our logical qubit, then they, by their votes, are going to say, hey, qubit 0 is in the wrong state, or our logical qubit is in the wrong state, even though it isn't. Everything else is in the wrong state. So this question is getting at where exactly that line is. And so essentially all we need to know is what is the majority of 100 qubits. And once we have a majority of errors, then our error correction is going to fail. So in this case, 50 is, well, it's not quite a majority, but that's where we will start getting failures in our error correction, is when 50 out of 100 qubits experience errors, and then when that happens, the majority vote is now wrong. And so it will correct qubit 0 into the wrong state, and so our error correction failed because we didn't end up with the state that we wanted for qubit 0, or the logical qubit. So are there any questions about questions 1 through 5 before we switch over to the notebook? All right. Then let's take a look at the notebook. As usual, make sure to run this first cell here. And in the meantime, we will get started reading the notebook here. So in this section, we are going to implement and explore a 3-qubit phase flip error correcting code. It's very similar to the bit flip code, but it corrects a different kind of error. So bit flips, remember, are when our 0 state is spontaneously or automatically transformed into the 1 state, and the 1 state is transformed back into the 0 state. So it's like us accidentally applying an X gate. A phase flip error is when the 0 state stays the 0 state, but the 1 state goes to the -1 state, which we know a gate that does that, which is the Z gate. So a phase flip error is like us accidentally applying a Z gate. So we are going to see how we can correct for those types of errors using a very similar circuit to the bit flip error correction circuit. So the first step, just like with the bit flip error correction, is encoding. So we just need to create a circuit with 3 qubits. Oops, I don't know why that happened. We need to create a circuit with 3 qubits. The 1 classical bit is handled separately. And then we're going to want to create entanglement between qubit 0 and the other qubits. And then finally, we are going to put all of our qubits in equal superposition to correct the plus and the minus states from switching instead of the 0 state and the 1 state. Okay, so step 1 here, we are going to create our qubits. Come on. We're going to create our qubits by using the circ.namedQubit.range function. And we need to specify the number of qubits. Just going to close out of that. The number of qubits that we want to create, which in this case is 3. And then we need to specify a prefix, which will tell us how we're going to go about naming those qubits. So we can say prefix equals, I always go with Q. As usual, you can name them whatever you want. But yeah, that is it for creating our qubits. We created a list of 3 qubits that we can use later. And then to create our circuit, we can just do circ.circuit, and that will create a quantum circuit that we can apply all of our gates to. Then we are going to entangle the state of Q0 with the other two qubits. So to do this, we apply two C0 gates. So I'm going to start typing here. The way we apply gates is we append it to the circuit, and then we need to specify what we are going to append. Well, we're going to append a C0 gate, so we do circ.C0, and then we want Q0 to be the control, so we can access our list of qubits and access the 0th qubit in that list. And then we need to target one of the other qubits. We're going to need to target both at some point, so let's just start with qubit 1. And then in this next line of code, we're going to do the exact same thing. So .append circ.C0. Again, qubit 0 is going to be our control, but now we want qubit 2 to be our target. So this code should look something like this, where first we apply a C0 gate with qubit 0 as the control and qubit 1 as the target. And then the second line of code, we have qubit 0 as the control and qubit 2 as the target. And make sure you run both of these cells. I almost forgot to run this first cell, but after you run this second cell, you should get a circuit that looks something like this. All right. Finally, we need to put all of the qubits in equal superpositions. So what we're going to do is we're going to apply an H gate to each qubit. So to our encode circuit, we're going to append. We need to apply an H gate to all of the qubits. So we're going to use our circ.h.on_each. And this will apply an H gate to every qubit that we put inside the parentheses, but we already have all of our qubits in a list. So we're going to put qubits, our full list of qubits, in those parentheses there. And then I'm going to print this out. Encode circuit. Hello? Why isn't it auto-completing? Did I spell something wrong? Encode circuit. Oh well. So if you run this, you should get something that looks like this. Okay. So are there any questions about step 1 here, this encoding step? Yes, this circuit is to correct from phase flip errors instead of bit flip errors. So just as a reminder, if we had a bit flip error, then the 0 state would be sent to the 1 state, and the 1 state would be sent to the 0 state. So this is called a bit flip. Bit flip. Okay, my handwriting's weird with the mouse, but whatever. For a phase flip error, that means that, remember when we write something like this, we refer to this thing in front of the 1 state as the phase. So a phase flip error would send us from the plus state to the minus state, and from the minus state back to the plus state. You could also write this as it sends the 0 state to the 0 state, and the 1 state to the minus 1 state. These two are actually the same. But these types of errors are called phase flip errors. Phase flip. Surely you can't tell I don't have my handwriting tablet right now, right? My handwriting's flawless. I don't know what you're talking about. Okay, so let's continue with step 2. In step 2, we want to do whatever that would introduce that noise. So in our case, we're going to simulate some noise, and we're going to do that with the Z gate, right? Because the Z gate is the gate that flips the plus state to the minus state, and the minus state back to the plus state. It flips the phase of the one state. So in our noisy, or as our noisy channel circuit, we're going to need to create another circuit, circ.circuit, and then we are going to apply a Z gate to simulate our noise here. So we're going to append circ.z, oops, that's an X, circ.z, and honestly, we can pick which gate or which qubit we apply the error to, because in reality, it can happen to any of these qubits, right? It's not only going to happen to qubit 0, because all of our qubits are equally bad. Just in this question, it wants us to simulate a phase flip error on qubit 0. So in this case, we're going to pick qubit 0. But I will say that there's nothing special about the other qubits. The other qubits might also experience phase flip errors. And we could simulate that as well by just changing this number in the square brackets here. All right, so when you run this, you should get a circuit that looks something like this. It's just Q0 with a Z gate applied to it, and it represents our noise kind of affecting our logical qubit. The next step is error detection. So in the detection part, what we're going to do is we're going to apply some H gates to try and undo the H gates that we applied before. Then we are going to undo the C0 gates that we did before. And if nothing happened in the middle, then we should end up with our original state. If something did happen in the middle, which we know something did, right? We applied a Z gate in between those two H gates. Then we're going to end up with a result that's slightly different, but that difference is going to let us know that we detected an error. Now, it's not going to let us know because that would require us to measure the state of the qubit, and that would destroy any state we were trying to protect. But it allows the next step to actually work and correct the error. So in our detection circuit, we are going to just create another empty circuit, and then we'll combine them all later. So circ.circuit. And then to our detection circuit, we need to do a couple things. We need to append some H gates, right? So we do circ.h. And again, we need to apply these to each of the qubits in our circuit. So on underscore each. And then we can put our list of qubits here. Then we can apply our C0 gates to undo those C0 gates that we applied at the beginning. And again, if there were no errors occurring in between those two H gates and the C0 gates, then the final state we end up with is going to be the exact same state that we started with. Otherwise, we are going to have the states of qubit 1 and qubit 2 change when we apply these H gates, and that will allow us to detect, well, again, it won't allow us. It'll allow the qubits to detect the error and correct it in the next step. So, okay, we need to apply our C0 gates now. So we can do .append circ.C0. And we want qubit 0 as the control, so qubits 0. And again, we could start off with qubit 1 as the target. But then we're going to add another C0 gate, append circ.C0, where we have qubit 0 as the control and qubit 2 as the target. So notice how the detection circuit is the exact same thing as the encoding circuit, but backwards. So we're kind of doing the steps in reverse to try and undo the encoding step. And if this doesn't work perfectly, again, we will be able to detect the error. So are there any questions about steps 2 or 3 before we continue? All right, then let's take a look at step 4, which is our error correction step. And the way I like to remember what gate to use for the error correction step is it's qubit 1 and qubit 2 telling qubit 0 if it got something wrong. So qubit 1 and qubit 2 are in control, and qubit 0 is the target. And so we're going to want a gate where qubit 1 and qubit 2 can be the controls, and qubit 0 can be the target. And we have a gate for that. It's called a Toffoli gate, or a CCX gate, or a CC not gate. And we are going to apply that where qubit 1 and qubit 2 are the controls and qubit 0 is the target. So for our correction circuit, we can again just create an empty circuit to start off with. So circ.circuit. And then we want to append our Toffoli gate, which in circ they call the CC not gate. So CC not, Toffoli, and CCX are all the same thing. They're different names for the same thing. And depending who you talk to, we were all taught different things. I call it the Toffoli gate, but apparently not everyone calls it that. So just note that they all mean the same thing. So the first 2 qubits now that we put are going to be our controls, and the last qubit that we put is going to be the target. So we want qubits 2 and qubit 1 to be our controls. So those are the first 2 qubits that we put inside those parentheses. And our target is qubit 0, so we put qubits 0 inside those parentheses there. I will point out that for the Toffoli gate, the order of the controls that you put here don't actually matter. Because they do the same thing, right? They both determine together if we apply the X gate to our target. And so having qubit 2 and then qubit 1 versus having qubit 1 then qubit 2 doesn't matter here because both of them are controls and they do the same thing. They work together. So having their order this way doesn't exactly matter. Whereas we could not switch qubit 1 and qubit 0 here because that would switch a control and a target, which are 2 completely different things. So the order of the controls doesn't matter, but the order of the target does matter. So the target definitely has to be at the one at the end, but your code will work equally well if you put qubit 1 as this first control and qubit 2 as a second control. Just thought I would point that out. So when you run step 4, you will get a circuit with just the Toffoli gate, and then we can move on to our decoding step. And in our decoding step, really all we're doing, the magic has been done in the first 4 steps. So all we want to do is measure the state of qubit 0 to make sure we successfully corrected that error there. So again, we are just going to create our circuit. So circ.circuit. Then we are going to append a measurement. Append circ.measure. And we only care about the state of qubit 0. We absolutely could measure the states of the other qubits, but they really don't matter because their whole purpose was to fix the state of qubit 0. And so in the end, we don't care what their final state is as long as qubit 0 is in the correct state. So we can run this here. We'll get a circuit with just a measurement. And that concludes our phase flip error correction circuit. So are there any questions about any of these 5 steps before we move on to the problems? All right. Then let's take a look. Yeah, let's take a look at we were working with the same. Yeah. We're going to continue working with this phase flip correction circuit that we created. We're just simulating it now and working with it, testing it out in different situations, stuff like that. Okay, so our phase flip circuit is just the circuit with all of those steps combined, right? So we are first going to want to encode. Then we are going to want to send it over our noisy channel, which we had in our noisy channel circuit. And then we do our error detection, which we had stored in the detection circuit. So detection circuit. And then we do our error correction, which we had in our correction circuit. Oops, no parentheses. And then finally, we're going to want to have our decode circuit. Decode circuit. There we go. So we just squish all of those circuits for the 5 steps together to create our full phase flip circuit. And then we want to simulate it. So we're going to need to create our simulator, which we can do. I'm going to call it sim. And the way we create our simulator is with this circ.simulator function here. And then we actually want to get some type of results. So I'm going to create a variable called result and set that equal to the result that we get when we run. So we do sim.run to run our quantum circuit on that simulator. And then we need to specify which circuit we want to run. In this case, it is the phase flip circuit. And we also need to specify a number of repetitions, which in this case, it specifies that it wants, I think it said 100. So repetitions equals 100. And do we need to complete this code in step 5? No, this is an extra cell here that you can delete if you want to. You could just get rid of that. All right. So if our code worked as intended, where qubit 0 started off in the 0 state, and we want to protect it from any phase flips, what do we expect to measure in like as the final state of this phase flip protection circuit? Well, we would expect to measure the 0 state because we should have protected it from any phase flips. So it shouldn't be the -0 state or anything like that. So if I run this, we get 100 out of 100 times the 0 state, which is exactly what we hoped would happen here. All right. Problem 1.2 wants us to make the logical qubit be in the plus state. So now how are we going to prepare it in the plus state? Well, we're going to want to set up our preparation circuit, which we can do with circ.circuit. And then to set up our logical qubit in the plus state, we're going to, so there are a couple different ways that we can do this, they're saying here. The traditional way is to apply a logical gate to all physical qubits after encoding. But that's not the way it's set up here. Here, what we are doing is we are going to apply it before the encoding. So it's slightly different, but the way we're going to do this is we're going to set up our logical qubit 0, in the plus state. So in our prepare circuit dot append, and how do we put qubit 0 in the plus state? We're going to apply the H gate. So we do circ.h, and we're applying that to qubit 0. Now, when we encode our circuit, the state that is going to be encoded is the plus state instead of the 0 state. So you could also do this by applying an H gate, or applying an H gate to every single qubit after the encode part. So that's why it's saying there are several ways to accomplish this. I prefer to do this first way, but in actual quantum computers, you would probably be expecting the noise as you're applying gates. And so if you want to protect that circuit, you would apply it during this noisy channel circuit, so that any errors that occur during that part are corrected for. Whereas if you do it at the beginning, then that's outside of the protection of this phase flip correction circuit. And so you might get errors by applying gates before this encoding circuit. But for us, it doesn't really matter. Looks like the rest of this is filled out for us. So now, what do we expect for our results? We would expect the plus state, right? The final state of the zero state, the 0th qubit, should be the plus state, because that's the state that we encoded, and that's the state that we're trying to protect. So we should end up in the plus state here, which we do see. But there's an issue, right? Using just this histogram here, we can't tell if it's the plus state or the minus state, because they're both equal superpositions. So in problem 3, we are going to add a gate to Q0 right before decoding to change its state into the computational basis, so the z-axis. So we are then going to have to draw conclusions about what state our qubit was in before the H gate. If we end up measuring the 0 state, then before the H gate, we must have been in the plus state, right? Because the plus state is sent to the 0 state. Whereas if we end up in the 1 state, then before the H gate, we must have been in the minus state, because the H gate sends the minus state to the 1 state. So I'm going to copy and paste this code from the previous step just to make our life a little bit easier. So take the code from problem 1.2 and paste it in problem 1.3, and then we can modify this to is this the best way to do it? I'm trying to think. Yeah, I think we can do this. So what we can do is, in between the correction circuit and the decode circuit, we're going to add an H gate, which we can do by just saying circ.h qubits 0, that applies an H gate to qubit 0, and then we need to add another plus sign after. So we have this big chain of addition. First we prepare, then we encode, then we send it over our noisy channel, we detect any errors, we correct any errors, we apply an H gate, and then we decode. So if we hope that qubit 0 is going to be in the plus state after our error correction circuit, then after we apply the H gate, we should get the 0 state, right? Because the H gate sends the plus state to the 0 state. So when I run this, we will see that 100% of the time we get the 0 state, which is a really good sign, right? It means that before the H gate that we applied near the end there, our qubit must have been in the plus state, which is exactly the state we wanted it to be in. So are there any questions about problem 1.2 or 1.3 before we continue? Scroll up a bit, sure. Is it this problem or the problem before? All right, I'll stay here for a second. All right. So let's take a look at problem 1.4. Problem 1.4 is asking if we get, if we have our logical qubit in the plus state, but there's a phase flip error on Q0 instead of Q1, will our code still work? I think I spoiled this a little earlier. Sorry about that. I got excited. But let's, again, copy and paste the code from the previous part and modify it to do what we want it to do. So I actually think I copied my code from problem 1.2. If you copied it from problem 1.3, watch out because you'll still have that H gate near the end here, which I don't know if we still want. Yeah, we can actually keep the H gate. So maybe I will copy and paste the code from problem 1.3 because the H gate will still help us figure out if a phase flip happened, which is very useful when we're trying to predict something like the plus state. So the thing we need to modify here is the noisy channel circuit, right? So we can just create a new noisy channel circuit. Noisy underscore channel underscore circuit is equal to circ.circuit. We're creating a blank circuit for our noisy channel circuit. Oops, let me zoom in a little. And then we can append to that. So noisy underscore channel underscore circuit dot append. What are we appending? We're going to append a Z gate. So circ.z. I also spelled the variable name wrong. Noisy. There we go. And we want to apply it to qubit 1. So I'm going to put qubits, square bracket 1, which will apply a Z gate to qubit 1. The rest of this code should be exactly the same. But we need to see if we still end up with the plus state in the very end. But again, we have this H gate right before we measure. So if we end up measuring the 0 state, that means our qubit ended up in the plus state. In grand reveal, we do get that our qubit after the H gate is measured in the 0 state, which means that before the H gate, it must have been in the plus state, which is a very good sign that our code is working. And problem 1.5 wants us to modify the code so the logical qubit is in the 0 state, but there's a phase flip error on both qubit 1 and qubit 2. So we are going to, again, copy and paste from the previous part and then modify what we need to. So we want to make it so that the logical qubit's in the 0 state, which means we don't need a preparation circuit at all, right? So we can delete it from here, and we can delete it from this addition of circuits down here, because we just don't need to prepare our qubit into any state because our qubit started off in the 0 state. So we can delete those from there. And then we also want to modify our noisy channel circuit so that there's a phase flip error on both Q1 and Q2. Well, we already have our phase flip error on Q1, so I'm just going to copy and paste this line and change it so that I apply it to qubit 2 as well. So I apply a Z gate to qubit 1 and another Z gate to qubit 2, and that simulates a phase flip error on both qubit 1 and qubit 2 at the same time. All right, the rest of our code should stay the same, But when I run this, that's not what I wanted to do. With the 0 state, we don't need this H gate, right? Because the H gate is only there to help us figure out if we're looking at the plus state or the minus state. So if I get rid of it now, because we're not looking at the plus state or the minus state anymore, we're looking at the 0 state or the 1 state. In that case, we end up with a histogram that looks like this, where 100% of the time we get the 1 state, which is really not good, right? That means that this majority decision went wrong. The majority of our qubits in this circuit experienced an error, and when that happened, the majority vote was that qubit 0 is in the wrong state, even though qubit 0 was in the state we intended it to be in. So they changed qubit 0's state because they were both tricked into thinking qubit 0 was in the wrong state, and so we ended up with the 1 state in the very end. So when the majority of our qubits have errors, we can no longer rely on the output of the circuit because it's probably wrong. All right, so that is it for the notebook. Are there any questions about the code we completed in the notebook before we switch back over to the homework quiz and wrap that up? All right. So switching back over to the homework quiz. Question 6 asks, which of the following changes would not make the phase flip code into a 5 physical qubit code? So in the notebook, we had 3 qubits, right? And the more qubits we have in our error correction circuit, the more qubits we can kind of tolerate errors for. So if I have only if I have 3 qubits, it's okay for one of the qubits to make errors, but if 2 of them makes an error, then again, the majority of those qubits get the wrong result, and we'll end up changing the state of qubit 0, even if we didn't mean to. Whereas if I had 5 qubits in my circuit, the majority there would be 3. So 2 qubits could now produce errors, and I would still end up with qubit 0 being in the correct state. So increasing the number of qubits will kind of give the qubits more wiggle room to make errors while still protecting the state of qubit 0. So which state would we not modify for this? Well, we are still going to want to create all of our qubits, so that's not going to change. We are still going to want to apply a CNOT gate where qubit 0 is the control and qubit 4 is the target. We're still going to want to apply our H gates to every single qubit, but this CC0 gate is kind of out of place here, right? This CC0 gate is where all of the qubits should come together and vote on what the state of Q0 should be. So if we had 5 qubits, we're actually going to need an X gate with 5 controls, or 4 controls in this case, because the 5th qubit is going to be the target. So we would have a gate that looks something like this, which does exist. It doesn't have a fancy name. I would just call it an X gate with 4 controls. But this way, all of the qubits are able to, I guess, share their opinions of what state qubit 0 should be in. So this CC0 gate just doesn't really make sense. So the correct answer here is in step 4, correction circuit.append. circ.cc0 with qubit 4 and 1 as the controls and qubit 0 as the target. That one would not make the phase flip code into a 5 physical qubit code. This fifth step I also think is a little strange, because in the decode step, we only care about the state of qubit 0, right? We don't really care about the states of the other qubits. So even though this measures all of the qubits, it's not necessarily wrong. It's just kind of pointless to measure the other qubits because they might not be in the right state. The only state we care about is the state of qubit 0. So you could measure all the qubits, but you don't need to. So this last line, I would also do a little differently, but it's not necessarily wrong. The only incorrect one is step number 4, applying a CC0 gate, because we would need that gate that had 4 controls to make sure all of the qubits are able to give their opinion on which state qubit 0 should be in. All right. Question 7, how many Hadamard gates are in the general circuit? So we can go back up here and walk through the steps and see how many H gates we applied. So when we initialize our circuit, we don't apply any H gates. So we're at 0 right now. And then we entangle the state of Q0 with the 2 other qubits, which doesn't require us to apply any H gates. But in this third part here, we are applying an H gate to each of the qubits. So we are at 3 H gates now. We then send it over our noisy channel, which doesn't involve any H gates. And then we move on to our error detection step, where we apply 3 more H gates. So we're up at 6 H gates now, because we applied 1 H gate to each of our 3 qubits. The error correction step doesn't have any H gates, and the decoding step doesn't have any H gates. So we have a total of 6 H gates being applied during this 3 qubit phase flip correction circuit. Are there any questions about question 6 or 7 before we continue? All right. Question 8. What percentage of the measurement results in problem 1.1 were the 1 state? So let's take a look at problem 1.1. We had the 0 state 100% of the time. So what percent of these are 1 states? 0% of these are 1 states. And that's us just reading off the histogram here in problem 1.1. Question 9 asks if a phase flip error is the same as an unintended Z gate, which of the following states is not affected by phase flip errors? So remember that our Z gate follows these rules, right? It sends the 0 state to the 0 state, and the 1 state to the 1 state with a negative sign in front of it. So right off the bat, we see that the 0 state is unaffected. But let's check these other ones, right? So the 0 state, this is the one we think is unaffected. The 1 state we see here is sent to the 1 state with a minus sign out front. So this state would be affected by the Z gate. And yeah, so that's not the correct answer here. The plus state would be sent to the minus state, right? Because the Z gate is a rotation around the Z axis. And so the plus state would be sent to the minus state, which would change the state. So this is also not correct. And then the minus state would be sent back to the plus state, which would also change the state. So that is not correct either. So the correct answer here is the 0 state would not be affected by phase flip errors. All right. Let's check out question 10, and then I will pause for any other questions. This asked, if we wanted to run Grover's algorithm for items represented by 90,000 logical qubits, error corrected with the code we've implemented in the notebook, how many physical qubits would we need? Well, each one of those logical qubits would need 2 other qubits to help protect it from phase flip errors. So we would have 1 logical qubit and 2 physical qubits, 2 more physical qubits, for a total of 3 physical qubits for each logical qubit. So we would just take 90,000 times 3, which is 270,000, which is a huge number of qubits, right? So there is still a reason we would want to reduce the errors that qubits experience, and it's exactly this reason. Sure, we could error correct every single qubit, but for that, we're going to need a whole bunch of qubits. We would need 270,000 in this case. Whereas if we move closer and closer to perfect qubits, we would need less and less extra qubits to help correct the errors of those logical qubits, which is much more attainable, right? We don't have a quantum computer with 270,000 qubits, and we don't have a quantum computer with even 90,000 qubits, but we're a lot closer to having 90,000 qubits than 270,000 qubits. That is very tricky to implement in practice, 270,000. Whereas 90,000, by comparison, is a lot easier to do. Still not easy, but it's easier than 270,000. And so there is still a goal of reducing errors in quantum computers to make it so that we don't need all these extra qubits hanging around and not doing anything. All right, so we can submit this quiz. And I hope I didn't get anything wrong. We got a 10 out of 10. That's good. So that is all from me. For people who are here, I will stick around for any questions. But for people watching the recording, thank you so much. And I will see you next week.